Hello dear friend, myself Prof. Sakburij K. Last lecture we can discuss definition of a degree of freedom. Actual definition of a degree of freedom. Degree of freedom of a system are defined as the total number of coordinates or independent quantity required to describe the position and configuration of the system completely. Then we can discuss some question on the basis of degree of freedom of a system. First question is, a cylinder is rolling without slipping on a straight road. What will be the degree of freedom of the cylinder? Answer is, as a cylinder is not slipping, it has only one degree of freedom. Then another question, how many degree of freedom a monochromatic gas has? Answer is, a monoatomic gas has a 3 translational degree of freedom. In this way, we complete this topic, degree of freedom of a system. Then we can discuss another topic, that is a new topic, is Mayer's relation. Mayer's relation. In this topic, we can discuss Mayer's relation for molar as well as principal specific heat. Here, we firstly consider 1 mole of a ideal gas that is enclosed in a cylinder by light frictionless um, airtight pistons. Then let here let here capital P, capital V and capital T be the pressure, volume and temperature respectively of the gas. If the gas heated so that its temperature rises by dt here but the volume remain constant, then the amount of heat supply to the gas, this heat supply to the gas is here dq, is used to increase the internal energy of the gas. Suppose this internal energy is dE. Since volume of the gas is constant, no work is done moving the pistons. Then amount of heat supplied to the gas is given by here. This become dq dq1 is equal to dE is equal to c suffix v into dv. Here c suffix v is the molar specific heat of the gas at constant volume. C suffix v is the molar specific heat of the gas at a constant volume. On the other hand, if the gas is heated to be the same temperature at constant pressure, volume of the gas increase by amount say dV. Volume of the gas increase by amount say dV. The amount of heat supplied to the gas is used to increase the internal energy of the gas as well as to move the piston backward to allow the expansion of the gas. The work done to move the pistons, this work done become here dW is equal to P into dV. Therefore, dq2 is equal to d plus dw is equal to, we can write here, c suffix p into dt. Here c suffix p be the molar specific heat of the gas at a constant pressure. Then from equation 1 and 2, here consider equation number here consider equation number 2. First is d Q1 is equal to dE is equal to Cv into dt. Here C suffix V is the molar specific heat of the gas at constant value, and another second equation is dQ2 is equal to dE plus dW. This become C suffix P into dt. Here C suffix P is the molar specific heat of the gas at a constant pressure. From equation 1 and 2 we get here C suffix P dt is equal to C suffix V into dt plus dW. Therefore, rearranging this equation, here C suffix P minus C suffix V into dt is equal to P into dV. From 1 mole of the gas, this C suffix P minus Cv into dt is equal to P into dV. Consider equation number 3 here. From the 1 mole of the gas, we can write value of N is equal to 1. Then according to ideal gas equation, PV is equal to nRT. Then this equation become here PV is equal to RT. Therefore, P into dV is equal to R into dt. Since pressure is constant, this value substituting equation 3, we get here C suffix P minus C suffix V, C suffix P minus C suffix V into dt is equal to R into dt. Therefore, we can write here Cp minus Cv is equal to R here. This equation is known as Mayer's relation between Cp and Cv. This equation is called Mayer's relation between Cp and Cv. Here Cp be the molar specific heat of the gas at a constant pressure, and C suffix V is the molar specific heat of the gas at a constant volume. Then also we can write here C suffix P is equal to M0 into Sp, and C suffix V is equal to, we can write M0 into S suffix V, where M0 is the molar mass of the gas and Sp and Sv are the respectively principal specific heat. Here Sp and Sv, S suffix P and S suffix V are the respective principal specific heat. Thus, we can write here according to this, uh, we get here M0 into Sp minus M0 into Sv is equal to R upon J, where J is the mechanical equivalent heat. J be the mechanical equivalent of a heat. Therefore, we can write here Sp minus Sv is equal to R upon M0 into J. Rearranging this equation, we get here Sp S suffix P minus S suffix V is equal to R upon M0 into J. Here capital J is a mechanical equivalent of the heat. Some question asked on this topic: derive the Mayer's relation for the molar as well as principal specific heat. Then another point we can discuss here: monoatomic gases, diatomic gases, and polyatomic gases. Firstly, we discuss monoatomic gases. Monoatomic gases. For a gas, for a monoatomic gas enclosed in a container held a constant temperature capital T and containing n suffix a atoms, each atom has only three translational degree of freedom. Therefore, we can write here. Therefore, we can write here average energy per atom is this become 3 by 2 k suffix b into T, and the total internal energy per mole is given by here E is equal to 3 by 2 n suffix a into k suffix b into T. This is the total internal energy per moles, and molar specific heat of a constant volume. Molar specific heat of a constant volume, this become, firstly we can write here C suffix v is equal to d upon dt. This also we can write here 3 by 2 n suffix a into k suffix b is equal to, this also become 3 by 2 into r. Using Mayer's relation, we can write here Cp minus Cv is equal to r. Then we calculate here Cp, then Cp is equal to r plus Cv. Therefore, Cp is equal to 5 by 2 r. 5 by 2 r's. And next one is a diatomic gases. In diatomic gases, second one is a diatomic gases. For a gas consisting of a diatomic molecule such as O2, N2, CO, HCl enclosed in a container held a constant temperature. Suppose this constant temperature is capital T. If treated as a rigid rotator, each molecule will have 3 translational and 2 rotational degree of freedom. According to the law of equipartition of energy, the internal energy of 1 mole of gas, this become the internal energy of 1 mole of gas, this become 3 by 2 n suffix a into k suffix b into T plus 2 by 2 into n suffix a into k suffix b T. Rearranging this equation here same base, then we can write here 5 by 2 into n suffix a into kb into T. The molar specific heat at constant volume will be the molar specific heat at a constant volume, this become C suffix v is equal to 5 by 2 into n suffix a into kb. Then we can write here 5 by this value is capital R, then 5 by 2 into r here. Cv is equal to 5 by 2 into r. Using Mayer's relation, Cp minus Cv is equal to r. Then we can write here C suffix p, that is the molar specific heat of the gas at a constant pressure is given by 7 by 2 into r. Then for diatomic gas containing non-rigid vibrating molecules, internal energy per mole is here for diatomic gas containing non-rigid vibrating molecule, internal energy per mole is E is equal to 3 by 2 n suffix a into k suffix b into T plus 2 by 2 n suffix a into kb into t, and another one 2 by 2 n suffix a into kb in t into capital T. Therefore, 7 by 2 base same, adding this term 7 by 2 n suffix a kbt, the molar specific heat at constant volume, this become c suffix v is equal to 7 by 2 n suffix a into k suffix b is equal to 7 by 2 into r. Therefore, cp is equal to r plus c suffix v is equal to 9 by 2 here. Here question asked on this topic: molar specific heat of monochromatic and diatomic gases at a constant volume and constant pressure. And another one is a degree of freedom. Here polyatomic gases. Third one is a polyatomic gases. Gas which have molecule containing more than two atoms are termed as polyatomic gases. Each molecule of the polyatomic gas has a 3 translational degree of freedom. Only linear molecule have a 2 degree of freedom for rotation. All other polyatomic molecule have a 3 degree of freedom for rotation. The number of degree of freedom f for the vibrational motion of a polyatomic molecules depend on the geometric structure of the molecule, that is the arrangement of the atom in molecule. Each such of degree of contributes average energy. This become here 2 into 1 by 2 into kb into t for kinetic energy, and potential energy term from the kinetic energy and potential energy term. Therefore, for 1 mole of a polyatomic gas, the internal energy become E is equal to 3 by 2 n suffix a into k suffix b into t plus 3 by 2 n suffix a kb into t plus f into 2 by 2 n suffix a k suffix b into t. Combine this equation 3 plus f, calculating this term 3 plus f into n suffix a into k suffix b into t. The molar specific heat at a constant volume and constant pressure are given by, here first molar specific heat at constant volume, this become c suffix v is equal to 3 plus f into r, and molar specific heat at constant pressure is given by c suffix p is equal to 4 plus f into r. Therefore, gamma is equal to c suffix p upon c suffix v is equal to 4 plus f upon 3 plus f. This is a adiabatic ratio in term of a degree of freedom for a polyatomic gases. Some question asked on this topic: determine the adiabatic ratio in term of degree of freedom for a polyatomic gases. Then, according to NCERT corners, specific heat capacity of a water, specific heat of a water for each atom in water, average energy is 3 k suffix b into t. Water molecule has 3 atoms, 2 hydrogens and 1 oxygen. Therefore, this become Q is equal to 3 into 3 K suffix B into T into N suffix A. This become 9 into RT. Therefore, C is equal to delta Q upon delta T is equal to 9R here. Variation of specific heat capacity of water with a temperature. We show this variation of specific heat capacity of water with a temperature. uh, this graph, uh, specific heat capacity versus temperature, this graph shown in this way. In this way we can complete this topic. uh, Meier's relation for molar as well as principal specific heat. Another one, monoatomic gases, diatomic gases and polyatomic gases. Today we stop here. Thank you.